All right, our next topic here is the Poisson interarrival process. So we talked about Poisson interarrival process. We're thinking about this as a process, a Poisson process on a one-dimensional Poisson process. And one way to think about a Poisson process, hold on, a little sloppy. Hold on. One way to think of a Poisson process, as we've already discussed, was in terms of throwing points down in an interval or on a line. But another way is to think of it as a sequence of arrival times or inter arrival times being the times between arrivals. So let A1 and A2 be the times of the first and second arrivals, respectively. So what we have is time 0. We have the time of the first arrival, the time of the second arrival. Okay. And we want to think about, well, what's the distribution of what's the joint distribution of the arrivals? So in order for, in this example, little a1, little a2 to be the first two arrivals, so the way we can do this is we can say, okay, let's consider small windows around a1 and a2. And then in order for those to be the first and second arrivals respectively, we need 0 arrivals here, 1 arrival here, 0 arrivals here, 1 arrival here. Okay. So in other words, the joint density times the width, right? This approximates the probability that A1 is within dA1 within a small region. A2 is within a small region. And in order for this to be true, what needs to happen, right? We need exactly 0 occurrences in the first A1 units. We need exactly 1 in the next dA1. We need 0 up to time A2, and then we need another 1. Okay, so we just have a bunch of non-overlapping subregions. So this is the product of probabilities by independence of the Poisson process. Oh, it's tedious right now. Okay, well, these are all Poisson. Rate lambda times the width of the interval. So this is a Poisson that equals 0. So this is e to the minus lambda a1. And then times the probability that 1. So we have lambda dA1 to the 1 e to the minus lambda dA1 over 1. And then we have e to the minus lambda, the difference, which is a2 minus a1 minus dA1. And then we have, try to fit this all on one line. Let's put this in there. Then what we have is we have lambda dA2 e to the minus lambda dA2. So when we do this, what happens? Well, there is a dA1 and a dA2. So we end up with e to the minus lambda so we get a lambda e to the minus lambda a1. And then there's a dA1. E to the minus lambda dA1, we can ignore that because dA1 is going to be small. E to the minus lambda a2 minus a1. So, and then we have another lambda. So lambda e to the minus lambda a2 minus a1 dA2. And I'm going to just put, so actually there's a e to the minus lambda dA1. That cancels, this cancels with this. And we still have e to the minus lambda dA2, but that's insignificant. Okay. We get rid of that. Okay. So this is the density provided that A1 is less than A2 by assumption, less than or equal to A2 by assumption. So let's define the inner arrival times. T1 is going to be the time between 0 and the first arrival. T2 is going to be the difference of the first two arrivals. So these are called the inner arrival times. Then in this case, what we want to do is we want to get the joint density of T1 and T2. And we're going to do this by using the change of variables for bivariate densities. Okay. And so when we do this, it's A1, A2, so we have to plug in the value, and then we have the determinant of dA1 dt1, dA1 dt2, dA2 dt1, dA2 dt2. So that's an easy determinant to take. That's just one. And so what we're left with is f of A1, A2, but we got to put, so this is that density as we just described, lambda e to the minus lambda T1, lambda e to the minus lambda A2 minus A1. Well, A2 minus A1 is T2. So what does that tell us? That implies that the T1 and T2, this breaks up as a product, right? This is the density of marginal density of T1, marginal density of T2. These are, this would be the marginal density T1, marginal density of T2. So these are T1, T2 are independent exponential lambda, right? So the Poisson interarrival times are just independent exponentials. This makes sense if we think through the if we think back through the memoryless property of an exponential. We already knew that the waiting time is how we actually derived the distribution, or the exponential distribution was, what is the distribution of the first arrival in a Poisson process? We showed it was exponential lambda. We also showed the Poisson process. Well, we know that the Poisson process by definition has independent increments, independent identically distributed increments. So once the first arrival occurs, let's say right here, everything after it looks just like a copy, an independent copy of the original Poisson process, which means that if we just ignore everything that happened before time A1 and we assume the process starts over, then the next arrival, the second arrival in the big process, but the first arrival in the new process where we ignore the history prior to A1, well, that's going to have an exponential lambda waiting time. And this is also tied in with the memoryless property of the exponential. It doesn't matter what's gone on so far in this Poisson process. We have an exponential waiting time, but if you cut it off and you say, let's start over from here, and let's just treat all of the arrivals from here on as the arrivals in a process, that process is a Poisson point process, a Poisson process with the same intensity. So all of these different ideas tie together: the independence of the increments in a Poisson process, the memoryless property of the exponential. They're all intertwined, and but we can see that there's a lot of different ways to derive this. We could have also derived this independence kind of just by reasoning through it. But if we didn't have that initial thought, then what we could do is exactly what we did here and process it through the change of variables formula.